Hello, welcome to another module in this massive open online course on the principles of MIMO, CDMA, OFDM wireless communication systems. So, in the previous lecture, we were looking at CDMA and how to generate the code sequences for CDMA, which stands for code division for multiple access. And we had said that the CDMA code sequences are generated as PN sequences. So, for CDMA, when we look at CDMA, the code sequence of CDMA is generated as a PN sequence, which stands for a pseudo noise the sequence. It looks like a random series of ones and plus ones and minus ones. This is generated as a PN sequence or a pseudo noise sequence. PN sequence means a pseudo noise sequence, and this is generated using an LFSR structure, which stands for a linear feedback shift register structure. So, the PN sequences, these are generated using the LF which is also the known as the linear feedback shift which is known as the linear feedback shift register structure. We had seen an example of an LFSR structure for D equal to 4 registers. We said that this is a maximal length linear feedback shift register, and it goes through all the possible states except the all 0 states. Therefore, it goes through 2 to the power of D minus 1 or 2 to the power of 4 minus 1, that is 16 minus 1 or 15 states, and the PN sequence that is generated by this LFSR, that is given as we had also derived that in the last lecture. The PN sequence from D equal to 4 linear feedback shift register, that is given as, well, 1 1 0 0 1 0 0 1 1 0 1 0. So, this is a sequence of length. So, this is the PN sequence that is generated by the LFSR, and the length of this PN sequence is equal to 15. So, this is the PN sequence that is generated by the linear feedback shift register, and the length of this PN sequence, that is equal to 15. We have 15 symbols in this PN sequence, right. Now, therefore, now what we are going to do, we have to convert this into a sequence of minus ones and plus ones. So, what we are going to do, we are going to digitally modulate this PN sequence by mapping, by modulating. We are going to use BPSK modulation. We are going to map the 1 information symbol 1 goes to a minus 1, this is the standard modulation, and information symbol 0 goes to plus 1. So, we are going to map 1, the information symbol 1 to a minus 1, to a voltage level. This is the typical convention. The information symbol 1 is mapped to the voltage level minus 1. The information symbol 0 is mapped to the voltage level plus 1. Therefore, now my PN sequence becomes, so my earlier PN sequence, let me write that, or let me write it over here, let me write that over here. Let me write that again. My PN sequence, information sequence is 1 1 1 1 0 0 0, 1, 0, 0, 1, 1, 0, 1, 0. Now, after modulation, this becomes, now after modulation, remember 1 is mapped to a minus 1. So, this becomes minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1. So, after modulation, this PN sequence becomes, this is the PN sequence after modulation. This is the PN sequence after modulation, and this sequence is given as minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, and the sequence is again of length 15, which remains unchanged, right. So, this is the modulated PN sequence. So, this is the PN sequence which is this is a pseudo noise sequence, which looks like a random sequence, a noise like sequence of plus ones and minus ones, which is used as a code in the CDMA system, the code by which the user signal symbol is multiplied. Now, to understand properties of CDMA better, let us examine the properties of this PN sequence. So, let us start examining the properties let us examine the properties of this PN sequence. Now, let me write this PN sequence. This PN sequence is minus 1, 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 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1. This is a sequence, as we already seen, this is a sequence of length 15. Now, let us calculate the number of plus ones and minus ones in this sequence. Let us calculate the number of plus ones and minus ones in this sequence. So, we have, so if we want to calculate the number of plus minus ones, first we have 4 minus ones here, 1 minus 1 here, 2 minus ones here, 1 minus 1 here, correct. So, number of minus ones is 4 plus 1 5 plus 2 7 plus 1 8. So, the total number of minus ones in the system total number of minus ones in this system is equal to 8. Now, let us calculate the number of plus 1 symbols in this CDMA, in this PN sequence. I want to calculate what is the total number of plus ones. So, total number of plus ones is we have 3 plus ones over here, 2 plus ones over here, another one over here, another one over here. So, there is 3 plus 2 5 plus 1 6 plus 1 7. So, total number of plus 1 is equal to 7. Now, if you see, we observe something very interesting. The total number of plus ones out of this 15 symbols, that is 15 plus ones and minus ones, we have number of minus ones is equal to 8 and number of plus ones is equal to 7. Therefore, what we have is roughly the number of plus ones and number of minus ones is equal. In fact, the precise relation is that the number of minus ones is exactly one more than the number of plus ones. So, what we observe is that the number of minus ones is equal to basically 1 plus the So, what we observe is the number of minus ones is basically 1 plus number of minus ones is 1 plus the number of plus ones, the number of minus ones is 8, which is 1 plus the number of plus ones, that is 1 plus 7. So, what you can see also is that the number of minus ones and number of plus ones are approximately equal, that is out of a length of 15, total length of 15, we have 8 minus ones and 7 plus 1. So, what we observe is that the number of minus ones and number of plus ones is roughly equal, and this is known as the balance property. This property is known as the balance property. So, what we have is number of minus ones is approximately equal to number of plus ones, and this is known as the balance property. That is approximately, if I take a length n PN sequence, approximately half of the symbols in the PN sequence are minus 1 and approximately half of the symbols in the PN sequence are of length are plus 1. So, approximately half and half are plus 1 and minus 1 each. This is known as the balance property, and more precisely speaking, the number of minus 1 symbols is exactly one more than the number of plus 1 symbols in the PN sequence. This is known as the balance property of the PN sequence. Okay. So, this is property number 1. Let us now look at property, another interesting property. Let us now look at property number 2. Let us now look at property number 2 for this PN sequence, and let us for this, let us look at the runs, what we call as the run. What is a run? A run in a PN sequence is a string of a run in a PN sequence. In a PN sequence, a run is a string of continuous values. Okay. So, let us look again at our PN sequence. Our PN sequence, what is our PN sequence? Our PN sequence is, well, our PN sequence is minus 1, minus 1, minus 1, minus 1, followed by 1, 1, 1, followed by minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1. So, this is my length 15 PN sequence. Now, let us look at the runs, that is there are strings, continuous strings of continuous values. I have one string of 4 minus 1s here. So, this is my first run of length equal to 4. I have another string of length 3, 3 1s. So, this is of L is equal to 3. I have another string of length 1. So, I have L is equal to 1. I have another string of 1s of length is equal to 2. I have another string of minus 1s of length is equal to 2. Then the rest of the strings, I have 3 strings of 1, minus 1, 1, and these are of length L equal to, each of these is of length L is equal to L is equal to 1. So, I have the first string which is of 4 minus 1s, so the length is equal to 4. I have the second string of length equal to 3, that is 3 ones, 3 consecutive plus 1 symbols. I have one string of length is equal to 1 which is a minus 1, one string of length equal to 2 of plus 1 symbols, one string of length equal to 2 of minus 1 symbols, again 3 strings of length 1 each, 1, minus 1 and 1. So, the total number of strings, if you look at the total number of runs or strings, total number of runs, that is the number of strings is equal to 1, 2 plus 1, 2, 3, 4, 5, 6, 7, 8. So, the total number of runs in this PN sequence, that is total number of strings of continuous values in this PN sequence is equal to 8. Okay. Now, out of these total number of runs, I have 4 runs are of length 1. Out of these total number of runs 8, I have 4 runs of length 1, correct. So, the length of the run is basically the length of the string, the length of the string is the length of the run, and we have 4 strings of length 1, which means we have 4 runs of length 1, and the total number of runs is 8. And now look at this, 4 is basically half of 8. So, basically which means that half of the 8 runs are of length, half of the 8 runs are of length 1. Now, let us look at the number of runs of length 2. We have 2 runs of length 2. We have 2 runs of length 2, which means 1/4 of 8, that is 1/4 of 8, 8 is the total number of runs, 1/4 of 8 is 2. So, 1/4 of 8, which is basically 1/4 of total runs are of length 2. So, what we are observing is half of the runs are of length 1, 1/4 of the runs are of length 2, and interestingly, if you look at this, you will further realize that you have one run of length 3. So, I have one run of length 3, which is 1/8 of the total number of runs. So, 1/8 of 8 is 1. So, 1/8 of total runs, 1/8 of total runs So, 1/8 of the total runs are of length 3. So, what we are observing is something very interesting. We are observing that half of the runs are of length 1, 1/4 of the runs are of length 2, 1/8 of the runs are of length 3, and if you have a longer PN sequence, we will have 1/16th of the runs of length 1/16th of the runs of length 4, 1/32 of the runs of length 5. In general, 1/2 to the power of n of the total runs of the total number. So, fraction 1/2 to the power of n of the total number of runs is of length n. So, what we are observing is the second interesting property, this is the run length property. Out of total number of runs, one over 2 to the power of n of total runs are of length n. right. So, what we are observing is, and this is known as the run length property of the CDMA sequences, which says that 1 by 2 to the power of n fraction of runs are of length n, which means half, that is 1 by 2 to the power of 1, or half of the total runs are of length 1, 1/4 of the runs are of length 2, 1/8 of the runs are of length 3, and so on. This is known as the run length property of the CDMA PN sequence. This is known as the run length property, and this is another important property of a CDMA sequence, which basically is the fundamental property it must obey if it indeed has to look at like a noise like sequence of plus and minus ones, that is a randomly generated sequence of plus ones and minus ones. And now we want to look at another property, that is property number 3, that is the third property. So, I want to look at another property, property number 3 of these PN sequences, and this is the most important property. This is known as the autocorrelation property of the PN sequence, and the autocorrelation of the PN sequence is defined as 1 over n summation over n C of n minus d, where this quantity d is the shift, this d is equal to shift, this quantity n is equal to the length of the PN sequence, the capital N is equal to length of and this is the autocorrelation. This is the definition of the autocorrelation, which is basically 1 over n summation of Cn multiplied by Cn minus d. So, what are we doing? We are taking each chip Cn, we are multiplying by the shift, by the chip corresponding to the shifted PN sequence. What is Cn minus d? Cn minus d is basically shifting the PN sequence by the quantity d, and therefore, we are shifting the PN sequence by this amount d. We are doing an element wise multiplication of these PN sequence and the shifted PN sequence by d. We are summing this element wise product, and then we are dividing by capital N, which is the length of the PN sequence. This is defined as this is known as the autocorrelation of the PN sequence. This is the autocorrelation of the PN sequence. Okay. Now, let us see what happens. Now, realize also that each Cn, each element Cn is either equal to plus or minus 1. Each Cn is either equal to plus or minus 1. Now, let us see what happens to this the behavior of this autocorrelation function of this PN sequence as a function of the shift d. Now, if d is equal to 0, then my autocorrelation is 1 over n summation n Cn minus d, but d is equal to 0. So, autocorrelation becomes 1 over n summation over n Cn into d equal to 0. So, this is simply Cn into Cn, but Cn into Cn is Cn square, which is summation over n C square of n, but Cn is plus or minus 1, which means C square of n is 1. So, this is simply 1 over n summation over n of 1. So, I will write the reasons. Since Cn equals plus or minus 1, C square n is equal to 1, summation 1 over n times 1, which is equal to 1 over n summation 1 n times is equal to n So, this is equal to 1. So, if D is equal to 0, the autocorrelation of this PN sequence is equal to 1. Okay. So, if D is equal to 0, if D is equal to 0, that is the autocorrelation or the self correlation of this PN sequence is equal to 1. Now, let us examine what happens if D is not equal to 0. For instance, let us take a simple example, let us consider D is equal to 2. Let us see what happens when D is equal to 2. Let us circularly shift this PN sequence by 2 symbols, and let us see what the value of the autocorrelation is going to be. Okay. So, I am going to write this sequence. So, I have C of n, which is 1, 1, 1, 1, minus 1, minus 1, minus 1, or my PN sequence is basically Cn is basically minus 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1. Now, I am going to circularly shift this by 2. So, I am taking this PN sequence and I am circularly shifting this PN sequence by 2 symbols. So, I am considering a shift of D is equal to 2. Therefore, this will become minus 1, minus 1, minus 1, minus 1, 1, 1, 1, followed by minus 1, 1, 1, minus 1, minus 1, 1, and this last symbols will come to the front because this is a circular shift. So, this is this. So, I have the sequence, I have the circularly shifted sequence. Now, I have to take the element wise multiplication and I have to take the sum, which is going to be minus 1 into minus 1 is plus 1, plus minus 1 into 1 is minus 1. So, minus 1, and calculating this way plus 1, plus 1, minus 1, minus 1, plus 1, minus 1, plus 1, minus 1, minus 1, minus 1, minus 1, plus 1, plus 1. And now, if you take the sum of all these things, you will see I have 1 minus 1 is 0, plus 2 minus 2 is 0, 1 minus 1 is 0, 1 minus 1 is 0, minus 3 plus 2, and this sum is minus 1. The element wise sum is minus 1. And now, dividing by n, therefore, the autocorrelation, now I am taking the element wise sum and now I have to divide by n. So, therefore, the final autocorrelation will be equal to minus 1 by n, which in this case n is equal to 15. So, this is minus 1 by 15. And what we are observing is something very interesting. We are observing that if the autocorrelation, if D shift is equal to 0, then the autocorrelation is equal to 1. For any shift other than 0, the autocorrelation decreases drastically. It is minus 1 divided by n. So, the autocorrelation property can be summarized as follows. The autocorrelation property of the PN sequence autocorrelation property of p-n sequence. If d equal to 0, autocorrelation is equal to if d is not equal to 0, autocore is equal to minus 1 by n. So, for any shift non-zero, so for a 0 shift the autocorrelation is 1, for a non-zero shift the autocorrelation is minus 1 over n. We had seen an example of this by considering a shift of d is equal to 2. Therefore, what you can see is something very interesting. As soon as the shift moves away from 0, the autocorrelation decreases drastically, it becomes minus 1 over n, which means as n increases, remember n is the length of the spreading sequence or the p-n sequence. If n is large, then 1 over n is small, which means 1 over n becomes progressively is approximately equal to 0 for large n, which means the autocorrelation of this p-n sequence for any shift other than the 0 shift is approximately equal to 0 for a p-n sequence which are large length n, which is a very desirable property as we are going to see shortly or in the subsequent modules. So, what happens is if n this is approximately equal to 0 for large n, or the p-n sequence decreases as 1 over n with large n. Therefore, I can plot this autocorrelation, the autocorrelation function of the p-n sequence. It looks like this, that is at 0 this is equal to 1, but away from 0 what happens is this autocorrelation it falls sharply, and this is equal to minus 1 by n. So, the moment I have any other shift other than the 0 shift, the moment I have any other shift other than the 0 shift, this autocorrelation falls sharply. So, this is the autocorrelation property of the p-n sequence. This is a plot of the autocorrelation. This is a plot of the autocorrelation of the p-n sequence. So, for a 0 shift the autocorrelation, so this autocorrelation equal to 1 for a 0 shift, and for any non-zero shift, for any shift other than 0, that is for any non-zero shift, it falls to 1 by n, which is approximately equal to 0 for a large n. So, the autocorrelation property of the p-n sequence states that the autocorrelation is equal to 1, or the self correlation is equal to 1 for the 0 shift, but for any non-zero shift the autocorrelation is minus 1 over n, which is approximately equal to 0 for a large n. And these are the 3 salient properties of the p-n sequences which are used in a CDMA system. One is the balance property, 2 is the run length property, and third, the most important property, is the autocorrelation property, which we are going to see will help us in extracting the multipath components in the wireless channel in a CDMA system, and that gives rise to the multipath diversity, and this is a very important property of the p-n sequences in a CDMA system. So, this module, which deals with the properties of the p-n sequences, we will stop here and continue with other aspects of the CDMA system in subsequent modules. Thank you very much.